Hello, chemistry students. This is lesson 10.5, where we're going to take a look at Avogadros law and the ideal gas law. So our objectives are for you to state Avogadros law, and then to solve various gaseous system problems using the ideal gas law. And we're going to review the conditions where gases do and do not behave ideally. Let's get started.
Alright, so here's a list of the individual gas laws that we have covered so far. If you want to write them down again, go ahead, but you should have them written down in your notes already, but if you don't, now's a good time to write them. So of course we have Boyle's law, which does pressure and volume equal to each other, and the held constants are your number of particles and your temperature.
And I know some of my students will get confused by this, but there's four major gas variables: pressure, volume, temperature, and number of particles or moles. Whatever variables are not in the equation for the law, that means they need to be held constant. So if we're looking at the pressure-volume relationship, you have to hold the number of moles constant, and you have to hold the temperature constant in order for that law to apply. It needs to be those conditions.
All right, for Charles's law, of course, it's volume 1 divided by volume 2, or temperature 2, and then it's volume 2, temperature 2. Held constant, again, are your number of particles and pressure. For Gay-Lussac's, we have pressure divided by temperature, and again, for this one, it's number of particles and volume held constant, and then for the combined, the only thing held constant would be your number of particles. So let's go look at the new...
Well, before we do that, Mr. Hunter, let's just look, what do we see as the one common thread here in the things that are held constant in all of these individual gas laws?
That would be our new gas law. We have a number of particles that are being held constant. So obviously, we do want to figure out how to use the number of particles.
Right, because sometimes we do need to change the number of particles in the gaseous system, and if that requires a calculation of a new constant or whatever every single time, that's not going to work. So the ideal gas law gets around that problem and kind of brings the number of moles into play as a usable variable as well. So let's take a look at that. So the first law that brings the number of moles into play was actually originally a hypothesis. It was proposed by Amadeo Avogadro, the one who the 6.02 times 10 to the 23rd is named after. In his law, which was originally a hypothesis, he said two equal volumes of gas under the same temperature and pressure will contain equal numbers of particles or equal moles. They didn't have the concept of moles back then, but now we say moles. So in an equation, what this looks like is the volume per number of moles is a constant. In other words, the volume and number of moles are directly proportional. If you add twice as many particles to the gas and you keep the temperature and pressure the same, the volume of the gas is going to double.
So like before, we have one side equal to a constant. Of course, the same sample kept under constant conditions would give you the equation V1 divided by N1 equals V2 divided by N2. So again, same type of equation as before, and as you can see from the graph, if we increase the number of moles or particles, of course our volume will also increase, making Avogadro's law another directly proportional law.
So one of the uses of this law when it first became a law was in determining the relative masses of atoms and molecules, which has always been problematic until more recently. So what they would do is take two different gases, and they put them in a rigid container that had the exact same volume, and they would carefully adjust the pressure until they had matching pressures, so that in these two samples of gas A and B, they had equal volumes and equal pressures. And that law is telling us then that under those conditions, the number of particles are equal. So then they would carefully mass the sample and subtract off the mass of the container, and then they could compare them. So let's just say in this example that gas A has a mass of 10 grams, and gas B would obtain a mass of 30 grams. So if they contain equal numbers of particles, then this is telling us how heavy one particle is relative to the other one. So that you could infer from that then that B's particles are four times on there? Sorry.
Okay.
3 times, I can't do simple math evidently, 3 times as massive as A's particles. And then if you know the mass, you know the exact mass of A, you could just triple it to get the mass of B. And this was very helpful in obtaining the atomic masses of the different elements on the periodic table, which they were around the time this law was proposed in the early 1800s, working out kind of what the average atomic masses are. Any gas you could vaporize then, or any element you could vaporize, you could use a technique like this in order to obtain its relative mass.
So listed here now is the ideal gas law, and they took all of the 4 gas laws that we currently talked about, Boyle's, Charles, Gay-Lussac's, and Avogadros, and we can combine them into one gas law. And in science, that is the best thing you could ever do, because if one law can explain 5 laws, that's a good law. So, with that,
so we combine all of those kind of into the same equation, and they've not kept K all by itself in the equation. Normally, the way it's written, you see pressure and volume on one side are equal to number of moles multiplied by temperature, and then you need this proportionality constant to make both sides equal. And this new constant, they decided, because it was so important, it got its own letter. So normally in the equation, instead of NTK, and they rearrange it for some reason, they put it in the middle now.
No, it's a good way.
PV equals nRT, which kind of rolls off the tongue nicely. Yeah. Where pressure, volume, number of moles, temperature, and R is what we call the ideal gas constant.
Yes, and then R, the value for R is 0.08206 liters times atmospheres divided by moles Kelvin. And this is an important thing to take note of. These units here are the units you're going to have to use for your pressure, volume, N value, which is normally moles, and temperature is Kelvin. So if you give something that has milliliters, kilopascals, and number of particles, you would have to convert them to liters, atmospheres, moles, and Kelvin, respectively.
Or calculate a different version of the constant, which is, also possible, but it's usually the way that we teach it is just what Mr. Hunter said. We have you change everything to the units that are in the constant. Otherwise, the units won't work out in the problem.
Okay, let's take some examples of these last 2 gas laws. So before we do these examples, we've talked about this in class a little bit, that real gases are not actually ideal. Real gases behave like ideal gases under most normal conditions. The assumptions, of course, that we make about these ideal gases are that the particles have no volume, the gas particles do not interact with other gas particles.
So they don't tend to stick to each other or repel away from each other. When they interact, it's much like two ping pong balls. They just have an elastic collision and go about their way.
And then lastly, gas particles are in a constant random straight line motion, only interrupted by collisions. But we know that the above assumptions are not entirely true, that real gases, when you put a lot of pressure on them or lower the temperature, they're either going to freeze, because gases do turn into liquids and liquids turn into solids, and of course, if you pressurize something enough, the gas particles will turn into a liquid or a solid based on that. So they will not.
When it starts acting like a liquid, then it stops acting like an ideal gas.
It's no longer a gas at that point.
So when you get to those extreme conditions, the calculations that you get from the ideal gas law a lot of times aren't what we actually see. If you chill helium to close to absolute zero, it's probably not going to have the pressure and volume that you would predict, because it's now a liquid.
All right.
Or at least liquid-like.
All right, now let's go look at those example problems.
So here's 2 sample ideal gas problems. I think if I was you, I would turn over my note sheet and write these down on the back. And I don't know whether you have to write it word for word, but at least write the variables that we're working with. So we have a sample of nitrogen gas, which of course the first thing you want to note is that it is N2, not N. It has a volume, 5.56 liters at 0 degrees Celsius, and a pressure of 1.50 atmospheres. And you're asked to determine the number of moles of nitrogen in the sample. So the first thing we have to realize is we cannot work with the Celsius temperature. We need to change it to Kelvin. And of course, we just adding 273 we can rewrite that as 273 Kelvin, which it would be equivalent to 0 degrees Celsius. Now we would begin with our ideal gas law, PV equals nRT. We're going to ask ourselves which variable we're supposed to find, and you can see that would be number of moles, which is abbreviated N, so we need to solve that equation for N. So that means N is equal to PV divided by RT. Then we substitute in the values that were given. Pressure is 1.50 atmospheres. We don't have to convert that because atmospheres is the unit of the ideal gas constant, times the volume of 5.56 liters. And that all gets divided by the ideal gas constant, 0.08206, and that's liter atmospheres per mole times Kelvin. And that's all multiplied by the Kelvin temperature, which is 273 Kelvin. So when you get this set up, and I highly encourage you to do it the way that I have, where we rearrange the equation first, then put in the variables so you don't have to write those numbers in their units multiple times as you're solving it. Then check the units to see if they cancel. So atmospheres here, atmospheres cancels itself out. Liters up there, liters in the constant cancels out. Then we have Kelvin over here and Kelvin on the bottom there.
So reciprocal moles means you have moles,
yeah, we have
as your new...
1 over moles. That means moles is the unit, and that's the way it should work out. The only unit left is the unit we want on our answer.
And it comes out to be 0.37 moles using...
Because 100, actually they all have 3.
372.
0.372 moles. Okay, second example. So this one is asking us to predict the pressure. Go ahead, Mr. Hunter. My voice is giving out. You can.
So this one's asking you to predict the pressure. Given the following example or following conditions, you have 2 moles of methane, which is CH4, which not that matters for this question, in a rigid 5-liter container at 100 degrees Celsius, which of course would be 373 Kelvin. So to set this up, it would be 5.00 liters times P, which equals 2 moles times the ideal gas law times 373. So if you wanted to solve for this equation, then, I don't know if you want to write that down first. 2 moles times R.
Six, right?
Yep, 6. And then lastly, times by 373 Kelvin. And we can let you do the algebra at home. Algebra is not what we're teaching you in this class. That's what algebra class is for. If you don't know how to do the algebra, please see us for help, or your math teacher. Solving for P, we find that the answer is 12.2 atmospheres.
However, if I look back up the problem, it asks us to predict the pressure in kilopascals.
All right, so you take 12.2 atmospheres, you multiply it by 101.3 kPa, divide it by 1 atmosphere, and you'll find you have a rather large answer, which is acceptable, of, 1,240 using correct sig figs. I missed that part when I was doing the math.
It's easy to do, so make sure you read the question carefully.
Okay, that's the last example for this. Have a good night.
Okay, to wrap up this lesson, we have 2 post-video questions for you. Number 1, what factors must be held constant for a gas sample when using Avogadros' law? And then number 2 is an ideal gas problem. So you have a 10.3 liter sample of gas, contains this many moles of gas at 295 Kelvin, and you're asked to find the pressure. So give that one a try, and we will talk about it next time.